Hi, IB, and happy homecoming, happy early Halloween. I hope that you guys had a good time on Saturday and now you are ready to buckle down and take some notes, ready for the week to come. We're now on the second day of applications of derivatives, so you guys can label this as your 3.2 rational functions. When you guys first learned about rational functions, this was in Algebra 2. Well, you really learned about them in Algebra 1, but you started to graph them in Algebra 2. And remember that a rational function is a fraction. So you're going to have a variable in the numerator and denominator, and you will have some asymptotes. So we have a little bit of vocabulary to get through first before we even start graphing. So how to graph a rational function using algebra and calculus without a calculator. The very first conversation that we had this year about calculus, it was that extension of algebra where you learn the basics of calculus in Algebra 1, and now we're going to extend it a bit further. So we are going to do a combination of things that you've learned in Algebra 1, like we have been all throughout the year so far, with some of the newfound concepts that we've done with calculus. For vertical asymptotes, just a reminder that vertical asymptotes are always written as x equals, and then whatever your, usually a is used for the point that you cross the x-axis, and in parentheses I'll say that is your x-intercept. The other piece to remember with a vertical asymptote is that the slope is undefined, and your vertical asymptotes occur at undefined values, basically, when you have an undefined value. So for example, you have a vertical asymptote when you have 1 divided by x, because you can't divide by 0. So this vertical asymptote is representing an undefined set, an undefined x value in your picture, or in your graph. If we have an undefined value, that means that your graph or your function cannot cross a vertical asymptote. So a function will not cross a vertical asymptote. On the other hand, a horizontal asymptote is very different. Horizontal asymptote, the definition and the proper way to find a horizontal asymptote is when you take the limit as x approaches infinity. And we are actually considering when x approaches positive or negative infinity. We're looking in both directions. We discussed limits and how to take limits in our last unit, and this is exactly why. So when we go to start graphing, we know what we're talking about when we say to take the limit of the function as x approaches positive or negative infinity. These are also obviously horizontal lines, and your function may cross it, so it doesn't give you an undefined value. So function may cross. All you have to know is that as x approaches positive or negative infinity, your function must be approaching whatever this horizontal asymptote is. So before it reaches infinity or negative infinity, it could cross it several times before it goes out to infinity. So we have a little review here of asymptotes, vertical and horizontal. We are not discussing slant asymptotes at this time. I know you guys did talk about that in Algebra 2 honors, but we are not discussing them right now. Taking the derivative. The reason why we take derivatives is because we are trying to lead into finding a maximum or a minimum or a point of inflection, which is what you guys were discussing last night or for your last set of notes. So we are going to take the derivative. If you notice, these vocabulary pieces are also steps in graphing a rational function. So step 1, we're always going to find the vertical asymptotes, and we're going to find the horizontal asymptotes. Then we're going to find the derivative. When you take the derivative, we are going to start by setting it equal to 0. And that way we can set up our sign diagram. So set your derivative equal to 0 and set up your sign diagram. And when I say sign diagram, that is SIGN diagram, not the trig function for our rational functions, all right? So set up your sign diagram. Include stationary points and vertical asymptotes in the sign diagram. So you are going to be looking for points of inflection. Stationary points is when your first derivative is equal to 0. We will look for your second derivative equal to 0 as well. So that's going to be your next step. Okay. And we are also going to include our asymptotes in our sign diagram, which is different than what you guys were doing the other night. You were not including asymptotes because you weren't talking about rational functions. So rational functions have both asymptotes, so we do want to include both of them in our sign diagram. So we are going to go ahead and put on here our first and second derivative equal to 0. I'm going to underline vertical and horizontal asymptotes. Vertical asymptotes only. We don't need the horizontal asymptotes because we're just talking about our x values. And we'll get to see what that looks like here in just a minute. And then from that sign diagram, we'll have to determine the increasing, decreasing intervals, the maximums, minimums, any horizontal points of inflection. And we'll have to find the points. So find the actual coordinates of those different points where you have a max, a min, or a point of inflection. So we do want to have those coordinates because we are about to put all this information on a graph so that we can actually see what this function looks like. So step 1, vertical asymptotes, horizontal asymptotes. Take derivative, take the second derivative, include all those points in the vertical asymptote in your sign diagram, and then we can determine what they actually are. And last but not least, if there are any x or y intercepts, we do want to find them. This is a jot back to Algebra 1. An x-intercept is found when your y value is equal to 0. So to find the x-intercept, set your y value equal to 0. To find your y-intercept, we set our x value equal to 0. And again, hopefully this is review. That little spot is. And then graph, including everything that you just did from above. So really you have 6 steps, some of them more familiar than others. These 3, 4, and 5, these steps right here I'll spend a little bit of time on because those are some of the newer ones to us. All right, let's go ahead and try an example. So let's take a look. Example of graphing a linear divided by a linear function. And I'm going to do some math up here, and down below I've got just a graph set up, ready to go. So if you guys want to have a graph, whether you have graph paper or whether you just jot a nice neat x and y axis, go ahead and have that somewhere else on your paper. And a linear function, that's just like y equals mx plus b, right? So we just picked 2x minus 3. That's our first linear function. That's g of x. And then x plus 2, that's our h of x. Let's go back to our steps. My steps tell me that first I should find my vertical asymptote, second my horizontal asymptote, and then third we'll take the derivative. So let's go ahead and do that. I'm going to use black. So step 1, vertical asymptote, and I'm going to shorten that by just saying VA. To find a vertical asymptote, we take the derivative, because remember, vertical asymptote, those are undefined values. Well, how would a fraction be undefined? A fraction's undefined when your denominator is equal to 0. So we take the denominator and set it equal to 0. And that allows us to find that our vertical asymptote is at x equals -2. First piece of information, we've got it. Step 2, horizontal asymptote. So you guys learned a few tricks, and I'm going to recap those tricks for you guys here. Your horizontal asymptote is the limit as x approaches positive and negative infinity and of your function. So of the 2x minus 3 and divided by x plus 2. Now you guys learned, and I'll put this over here in green. You guys learned that if you had a, I'm going to put a little brain bubble over here because this is a review from a while ago. Okay. Let A be just an integer. So I'm going to say an element of the integers, and this Z with a double line means integers. Okay, so let A be an integer. If you guys had, let's say, an integer divided by a variable, you guys learned that your horizontal asymptote would be y equals 0. Because when you're dividing an integer by anything that's larger power, because remember your degree of x is 1, so if I have a constant that's divided by a variable with a degree of 1, well, I'm going to wind up with 0. So I'm going to have my y is equal to 0. The second one that you guys learned, I'm going to leave a little space for myself, is that if you have any kind of function that has equal powers, so x to the first over x to the first, what you wind up getting is whatever the coefficient is. So let's say a is my coefficient. Okay, we're just pretending like a is an integer here. I made it up. So then my asymptote would wind up being, well, x divided by x is 1, so all I'm left with is a. Okay, those were your two biggies. And then your last one was if you wind up having a power in the numerator that was higher than whatever the degree was in the denominator, that's when you actually divided and you wound up getting some kind of slant asymptote, or yeah, that's what you guys basically were doing back in Algebra 2. We will not spend a whole lot of time on this scenario right here. We are going to focus mostly on if your numerator is a smaller degree or if you are equal degrees. Okay, but that I just want to bring back because you did learn that back in Algebra 2. The more sophisticated way of doing it is to simplify the limit by dividing through by the highest power. So if I have my limit as x approaches infinity, okay, and I have, oops, excuse me, didn't finish that one out, infinity, I'm going to take 2x, divide it through by my highest degree, which is x, and then minus 3 divided by x, and then divide by my denominator as well, divide that through by x, and add that to 2 divided by x, okay? If I do that, what winds up happening is I can take the limit of each of these separately. Well, my limit here, if I just simplify this, this winds up being 2 minus, if I have a constant divided by x, that is going to go to 0 as x approaches infinity, because as x approaches infinity, if your denominator gets larger and larger and larger and larger and larger, 3 divided by a very large number will go to 0. So that will be 0. X divided by x is 1, plus another constant divided by x as x approaches infinity. That will also be 0. So 2 minus 0 over 1 plus 0, you just wind up with 2. If you guys look back at the trick, the short way that you guys learned in Algebra 2, remember if you guys have the same degree in the numerator and denominator, so I have an x divided by an x, I just take the coefficient, which is 2. Well, there's my 2. So both ways, either way is acceptable. Since it's a horizontal line, remember your equation is going to be y equals 2. And that step will go faster once you start to practice a few of them. But there's my second step. And then my third step is to take the derivative. Well, this is a quotient, so when I take the derivative, I will have to use the quotient rule. So let's try that. The derivative of the numerator is 2 multiplied by the denominator. Subtract the derivative of the denominator, which is 1, multiplied by the numerator. And then I divide by my denominator squared. And I will simplify this a bit. I'm going to go ahead and scroll down. If I simplify this, I will get 2x plus 4 minus 2x plus 3 divided by x plus 2 squared. And remember what I want to do with this. I want to actually I want to find my stationary points, right? Or my critical points. So I will actually be setting this equal to 0 here in just a moment. Well, 2x minus 2x, that cancels. So I just have 4 plus 3, which is 7, over x plus 2.